Hello, my name is Zoe Rosenburg and I go to Rutgers University, New Brunswick in New Jersey. My project is modeling pair instability supernova. So first of all, what is a supernova? We think of there being two types, usually two main types. One is a core collapse supernova, which is when a very big star at the end of its life dies and explodes, and one called a thermonuclear supernova, which is when a smaller star gains too much mass from the outside and explodes. So a pair instability supernova is a theorized third type of supernova that hasn't actually been observed yet. And a pair instability supernova is called that because the actual explosion of the supernova starts to occur due to this reaction where particles of light, or photons, will interact with each other and they'll form pairs of electrons and the antiparticle to an electron called the positron. They form pairs, and that's why the pair instability supernova has that name. So my project has to do with making a model or a simulation of this type of supernova explosion, but it actually doesn't start at the explosion, it starts right after the explosion. My initial conditions are from a past graduate student here at NC State who ran a simulation of a parent star for one of these explosions up until right after the explosion. And my simulation picks up where theirs left off about 33 seconds after the initial explosion. And using this code called VH1, stands for Virginia Hydrodynamics 1. Hydrodynamics sounds scary, but it just has to do with the motion of fluids, and when we're dealing with a supernova remnant, there's a bunch of gas from the star that's expanding out in space, and gas is a fluid, so that's how it has to do with hydrodynamics. So I use this code, and it allows me to put in different parameters like, let's say, density and pressure, velocity, and with those initial values, it can actually evolve the supernova remnant throughout time. And it'll give us back values, the same values that we put in, but for different later times in the evolution of the supernova remnant. So as you can see in this cartoon, there are kind of three little supernova remnant pictures. And the first one is smaller, and then it gets a little bit bigger and a little bit bigger. So this is kind of what it would look like visually to see the code evolving the supernova remnant. So as you can see, I have values listed for different radiuses and different times. And these radiuses actually come from my code. I went in and picked out radiuses for these different times over the evolution of the code. And it'll just give you an idea of the scale, because the radius is just from the center of the supernova remnant out to one of the sides. As of right now, my project doesn't actually look like this because I'm working in one dimension, so that just gives us line graphs, and one dimension just means that it assumes that the whole supernova remnant is spherically symmetric. But I will be moving into 3 dimensions, which can actually show us something that looks more like this little cartoon, and it will also allow us to account for asymmetries in the supernova remnant. So the end goal of this project is to evolve the simulation out to a couple hundred years, and it'll give us an idea of what a pair instability supernova remnant would look like. This is super important because we don't actually know what a pair instability supernova remnant looks like yet, because like I mentioned, we haven't actually observed them in outer space yet. Up until this point, there haven't been any simulations of a pair instability supernova explosion through the remnant stage. I will also be evolving a similar model of a core collapse supernova remnant, because these are supernova that actually occur more commonly in our local universe. So by evolving a similar model of something that we know, I'll be able to directly compare what differences and similarities there are between this thing that we already know about and this pair instability supernova explosion, which we still don't know that too much about. So what I've done this summer is I've edited this code so that it can read in the initial data and work with that. And I also have edited the code so that it can now look at the elements that are present in the supernova remnant, and it can track where these elements are throughout the evolution of the supernova remnant. And it will also be able to look at where the elements are actually shocked in the supernova remnant. So right now, I'm in the process of moving from 1 dimension to 3 dimensions, and this is exciting because, like I mentioned, it'll be a lot more visually pleasing to look at. I'm excited to continue moving forward with that as the fall semester approaches. So to just look at a graph of something that I've actually done this summer so far, this is just an example of what it kind of looks like for the code with evolving the remnant. As you can see on the vertical axis, we have density, which is just how much material is present. And on the horizontal axis, we have radius. And the log in both the vertical and the horizontal axis just means that the range of the axis is much wider than it would typically be if you're looking at a typical graph. So what the graph means, looking at the first curve on the left first, is that at a smaller radius, you have a pretty high density. There's a lot of stuff in the center. And then as you're moving outwards to the right, you get slowly less stuff, and then the density drops a lot more, and you have a lot less stuff as you go out to the edge. And then the different colored curves in this graph are the values of density and radius for different time values as the remnant is being expanded in the code. So starting with the initial condition, the first curve on the left, and then when you move to the right, you're going later and later in time as the code runs and the remnant evolves. So as you can see in the last couple of curves on the right, there are some little squiggles as the curve goes downwards. And we believe that those are due to numerical noise in the initial data. And this is something that we have to go back and look at before we can actually finalize running the code in one dimension. But once we do that, we will be able to actually finalize one dimension. We're pretty close to that, which is really exciting, and then move on to 3 dimensions and do our comparisons with the core collapse supernova and what they look like. So my research this summer is a step in the direction to confirming whether or not some strange supernova remnants that we've actually observed could potentially come from the pair instability supernova mechanism. And this is super exciting to me because having the possibility to potentially actually see one of these is a really cool idea. If this happens and if we're able to actually observe one, it's going to provide us with an entirely new astrophysical object to observe with our telescopes. Regarding the CDSA program in general, I learned a lot this summer, both about research and just about how I operate with research as well. But one of the main things I learned is that research isn't a straight path by any means. A lot of times you might have to take some steps backwards or some paths that move out of the way, or even bang your head against a table a couple of times in order to finally move forward. But when you're able to, like when your code starts to work, or when you're able to present the stuff that you did to people who are really curious and excited about what you're doing, it all ends up being worth it. And it's been really great to be able to go through that process and to actually see the results. And I also really got to experience a sense of community with others who are passionate about astrophysics and about research this summer. So it's been a really great experience, and I'm really happy that I was able to spend my summer here at NC State. So thank you very much, and I hope that you enjoyed my presentation.